This video has been put together because Molly asked for some revision on velocity time graphs. Let's get revising. I'm going to divide the video up into two parts. By the end of this revision, part 1, I want you to be able to talk about this velocity time graph. When you've done that, we'll go through the answers in part 2 and set you one more question to think about. Velocity is a vector quantity. This means that it doesn't only have a size or a magnitude, like 4 meters per second is how fast something's going, but it also has a direction, forwards, backwards, up or down. Velocity is speed in a particular direction. So for example, to describe something as going plus 4 meters per second might mean that we're talking about something moving at 4 meters every second in a forwards direction. So when we look at velocity time graphs, we're looking at the motion of something. And anything that's above the axes would be moving in a positive direction, which might be forwards or up. Anything below that time axis would be an object that's moving backwards or down in the opposite direction. We're not going to worry too much about that first, we're just going to concentrate on positive velocities. So here we have an object that's moving forwards, a positive velocity of 4 meters per second. That velocity is not changing with time. It's a constant, fairly fast velocity of 4 meters per second. Now this horizontal line shows us we've still got a constant velocity, but now that velocity is a slower constant velocity of only 2 meters per second. And in this velocity time graph, the object isn't moving at all. The line is seen along the time axis where velocity is 0 meters per second. This is an object that's at rest or stationary. Now in this graph, velocity is changing with time. As time goes on, velocity is increasing. So the velocity is changing with time, it's increasing with time. This is an object that's accelerating. And the straight line shows us that it's accelerating at a constant rate. We can actually work out that acceleration as well using the gradient of the line. If we look at the y value of 10 and divide it by the x value of 2, 10 divided by 2 gives us a 5 meter per second squared acceleration. For people that like to see working out, I have written out all the working out that goes with this video, and if you would like a copy of that, you just need to ask me in class and I'll make sure you've got one to have when you watch this video again. So back to our velocity time graph. Now we still have an object here that's accelerating, and accelerating at a constant rate. However, the gradient is shallower here. And the gradient here can be worked out as 10 divided by 5, which would give us an acceleration of only 2 meters per second squared. Why does the gradient tell us the acceleration? Well, think about what acceleration is. The change of velocity in time. The y-axis is showing us the change of velocity, in this case from 0 to 10 meters per second, and the x-axis is showing us the time that takes. 5 seconds. So y divided by x is change of velocity divided by time, and that's acceleration. 2 meters per second squared, a constant rate of acceleration here. Now this graph also shows us an acceleration because velocity is increasing with time. But there's not a straight line now. This curve has a changing gradient, starting shallow and getting steeper as we move along in time. This is showing us that the rate of acceleration isn't constant. This is an accelerating object that's accelerating at a faster and faster and faster rate over time. Here we have a change of velocity with time, but this time, as time carries on, velocity is getting less and less and less. The object is getting slower and slower. So this is an object that's decelerating. It has a negative acceleration. The straight line shows us that that deceleration is at a constant rate, and we can still work it out from the gradient, 6 divided by 3. That would be 2 metres per second squared. But this would be minus 2 metres per second squared to show that it's a deceleration. So, to recap, acceleration is the rate of change of velocity in time. So from a velocity time graph, we can find the acceleration by using the y value divided by the x value, and that's the gradient of the velocity time graph. So have a go at working out the acceleration and the deceleration in this velocity time graph. Pause the video while you have a go and then come back for the answers. So, in the first part of the graph, we have an acceleration, a constant acceleration that can be found by doing 8 divided by 2. It's 4 metres per second squared. In the last part of the graph, we have a deceleration, a constant deceleration, which can be found out by checking how much time it's taken between 8 and 14 seconds, so that's 6 seconds, and then our y value of 8 divided by 6 will give us minus 1.3 metres per second squared for that deceleration. So we can work out the gradients, and that can tell us about acceleration and decelerations in a velocity time graph. But that's not the only thing we can use a VT graph for. We can also find the distance that an object has travelled. To find the distance, you need to work out the area that's underneath the line, between the line and the x-axis. Here I've divided that area up into a triangle up to the first 2 seconds interval of time, a rectangle between the 2 and 8 seconds, and a finishing triangle between the 8 and 14 seconds. The area of that first triangle we can work out from half base times height. So a half of 2 times 8, so that's 1 times 8, that's 8 metres that have been travelled in the first 2 seconds. In the next section of the graph, when the object is moving at the constant speed of 8 metres per second in the same direction forwards, we can work out how far is travelled by calculating the area of that rectangle. In this case, 8 take away 2 gives us 6 seconds of time along the base, and the height is 8 metres per second. So 6 times 8 gives us a total of 48 metres. The last triangle, using our half base times height method again, we've got half times 6 times 8. So that's 3/8, which is 24 metres that were travelled in that last 6 seconds of the journey. So let's recap. The speed is distance divided by time. So the distance is the speed times time. This means that we can use the velocity time graph to work out the distance. And the distance will be the area that's been enclosed by the line and that time axis. The best way to check that you've understood the ideas in the video is to have a go. So I've drawn this velocity time graph for you. This is a cyclist who's cycling away from their home to pick something up, and then they're cycling back home again. What I want you to work out are the accelerations, the decelerations, and the distances that have been travelled away from home and back to home. You should find they took a shortcut on the way home. How much distance did that save them? There's a challenge. I want you to try and have a go at working those out, and then join me in part 2 of the video when I'll go through all these answers and give you one more example question.